Hello and welcome everyone. In this video, we'll be creating a first-person physics-based character controller using fish networking and its recently released Prediction version 2 feature. Prediction version 2 makes prediction in fish networking easier and allows us to have smoother movement without really doing too much work, okay? As you can see, I have two players running. On the right-hand side, I will start a server and a client. And as you can see, I can move around, I can jump, and I can look up and down, okay? Now on the left, I'm going to start a client, and as you can see, I can move around, jump, and I can bump into other players. And since everything is physics-based, the movement and, the actions are replicated across the network, okay? So as you can see, I can push the server object, and if I go on the server, I can push the client object around. So as you can see, I can bump into it and it will replicate across the network. So let's push the player with the edge, and as you can see, it is replicated, okay? So let's get started on how to create something like this. So I have a Unity 2022.3.19 project that I just created, okay? And I imported fish networking and created two scripts, one called first person controller and another called network HUD. But I also created a scene, which I have here, which contains four objects: the main camera, the directional light, and the network manager. The network manager has the network manager component, the time manager component, the player spawner component, and a network HUD component. I changed the default tick rate on the time manager to 60 instead of the default 30, just for the sake of demonstrating the movement, okay? I also created a network HUD component, which just allows me to start and stop server and client, okay? Also, I have created a player prefab, which has a capsule collider, a rigid body component, and our first-person controller component, plus the network object component. One of the new things about Prediction version 2 is that you no longer need the predicted object component. You can simply enable prediction by checking the enable prediction checkbox here and select rigid body from underneath prediction type, okay? And also you will need a graphical object, which is basically the object that fish networking will try to smooth out across the network, okay? So as you can see here, I have a model, which is a capsule, and I have a visor, which is a cube, okay? I set the graphical object to be the model, which is the capsule, okay? And let's go inside our first-person controller and begin exploring how it works. So basically, we have a sealed class called first-person controller. It derives from network behavior. And we have a serialized field of type input action asset. Since we're using the new input system, we use input action assets, which are basically a collection of action maps which contain inputs, like for example the movement actions we have here, or the mouse actions, mouse axis actions, okay, like looking up, down, left, and right. And you can see this in the editor under the input folder. I have an input actions asset, which you can create by right-clicking, create, and selecting input actions. Okay, I have already created one, so let's check out how it looks. Let's double-click on it to open like the input action editor. I created an action map called player, which will have the player actions, and I have 5 actions inside of this map. Horizontal action, which is of type axis, and it has a keyboard binding of A and D. Vertical is the same as horizontal, but using W and S. Jump is of type button and has a space key binding. Pitch and yaw are axis, which have bindings to delta Y and delta X respectively of the mouse, okay? So we can look around. Now, once we have set up the input asset, we'll go back into Rider, and we have fields here which allow us to access the actions we have: horizontal action, vertical, jump, pitch, and yaw. Okay. Also, we have two references, one to our rigid body and another transform reference to our camera object. Okay. And then we have a field called movement speed, which is basically the movement speed of the character, and jump speed of the character. Okay, we have one here and another one here. Okay, now we also have a field called feet offset, which is how far are the feet from the origin of the object, and the feet radius, which is how wide or how big the feet of the character is. Okay. Underneath this, we have the ground layers field, which is which layers are considered the ground. So when we check whether we are landed or not, we have certain layers which we would like to consider the ground. Okay. We also have two fields down here, one called pitch sensitivity and yaw sensitivity. The pitch sensitivity basically controls how fast or how sensitive your character is to vertical inputs like looking up and down. And the yaw sensitivity is how sensitive your character is to rotation on the y-axis, or basically left and right. Okay. Also, we have a field here called renderers, which is an array of renderers. We will use this array to basically just hide our model when we are not, sorry, when we are the owners of the object or when we are the local player. Now, going down here, we have 5 fields, which are basically the primitive types of our actions. The horizontal field, which is the horizontal action value. Vertical, same as horizontal, but for the vertical axis. Jump, which indicates whether we are trying to jump or not. Pitch, which is basically the value of the pitch action. And yaw, same as pitch, but for the yaw action. Now, going here, we override fish networking's onStart network callback, and inside this callback, we will find our actions by name. Notice here I'm using find action for the sake of simplicity, but you usually use find action map and then find action, which is much more efficient. So usually you do something like find action map, player, and then find the action. But for the sake of this tutorial, and since we have only one single action map, I'm just going to use find action directly. Now we do this for the horizontal action, vertical action, jump, yaw, and pitch. Let's just organize this. Okay, and now as you can see here, we enable our actions one by one. This is useful in some cases where you have many inputs that you would like to enable at certain points. You can just enable the whole input action asset, which will recursively enable the input actions as well. But for the sake of demonstration here, I'm just going to enable each one manually. Okay. Then down here, we assign our rigid body reference to the get component, which basically finds the rigid body on our object. And then our camera is going to be the child named camera in this case. Okay. Now, beginning prediction stuff from here. We have our reference to the time manager, which is just a property on the network object, network behavior itself. We subscribe to the onTech and on PostTech events, and we have 2 handlers here. We'll get back to those later. Let's go and collapse them, and let's go to some important structs. Prediction version 2 basically follows the same idea of just having 2 structs, one for the movement data and one for the reconciliation data. So our movement data structure is going to derive from the iReplicate data interface, and we need to implement the methods getTech and setTech. Also, we have a method called dispose, which is used internally by fish networking. As you can see here, I have set the horizontal, vertical, jump, and pitch and yaw to be all read-only, since we are not going to modify this. This is just a micro optimization. Also, I set the getTech method to be read-only, again, a micro optimization. Now going down here to our reconciliation data structure, it's going to derive, or sorry, implement the iReconcile data interface. We have, of course, a field called tick, which is assigned by fish networking internally. we have position, rotation, velocity, and angular velocity. The position and rotation are, of course, the position and rotation of our rigid body, and velocity and angular velocity, again, are of our rigid body, okay? In the constructor here, we assign the fields and set tech to 0. Now, again, we have getTech, setTech, and dispose, and I have set the relevant fields and methods to be read-only, okay? Now, going back here, our movement data structure is basically going to be the structure which holds the inputs we are going to use for our character, okay? And the reconciliation data structure is going to hold the data that the client will use to correct discrepancies, okay? So when, for example, when moving, if the client for some reason tries to move in a different position or rotate in a different direction than what the server wants, it will be reconciled to the correct positions, okay? Now, going up here, let's collapse our structures here. We go to our onStartClient method, okay, which is an override. Now we check if we are not the owners. We disable our camera game object because we don't want to have multiple cameras enabled on the same game for different clients. And we try, otherwise, if we are the owners, we iterate over all the renderers we have and just disable them. This differs from game to game. You might want to keep this enabled, you might want to disable them, but for this tutorial we will be disabling them. Now let's go to our update method where we check if we are not the owners, we return or we don't do anything. But if we are the owners, we get the values of horizontal, vertical, jump, pitch, and yaw by reading the value of each action. In case of horizontal and vertical, we just say read value and pass in float as the generic type. And vertical, same thing. Now for jump, we say jump action.is pressed because it's of type button, and we check if it's pressed in currently, and we do a physics.checkSphere call, passing it the rigid body position and the feet offset, the feet radius, and the ground layers. The reason I have put the is pressed first is because the and operator, or the short-circuiting and operator, as its name suggests, short circuits if either of the conditions isn't true. So if jump isn't pressed, it doesn't evaluate this at all, which saves us just a tiny bit of performance. Now for pitch and yaw, we do like horizontal and just read them as floats. We have down here a bit of code we use to enable and disable the cursor. So we check if the escape key was pressed this frame, and we say if the cursor was locked, we unlock it and make it visible. Otherwise, we lock it and hide it. Okay, now let's collapse our update method and our onStartClient method and go back to our time manager event handlers. The first event handler we have is the tech event handler. As you can see here, it's very simple. We simply check if we are the owners. We create a new movement data structure. We pass in the current values of horizontal, vertical, jump, pitch, and yaw, which we collect in the update method, okay? And then we call the replicate method, passing in the movement data, okay? Otherwise, if we are not the owners, we simply call replicate with the default value of the movement data structure, okay? That's pretty much it for the tech event handler. Now let's collapse this and go back to the PostTech event handler. Here we check if the server has started. Starting from Fish Networking version 4, there is no longer an isServer or isClient properties. There is isServer started and isServer initialized. For this tutorial, and as a replacement for isServer, we use isServer started. Okay, now if the server has started, we go here and create a new reconciliation data structure, passing in the current rigid body position, rotation, rigid body velocity, and angular velocity. Okay, that's pretty much it for the PostTech event handler. Now let's go to the replicate method. The replicate method has a special signature required by Fish Networking, that is the movement data structure. If a parameter named replicate state, or just a parameter with a type replicate state, by default set to invalid, and a channel parameter set to unreliable by default. Okay, you don't need to set or supply these values because they are supplied automatically by fish networking. So yeah, you should leave them with their default values. Now, going here, we do some basic movement logic by basically first getting the rotation of the rigid body and getting the right and forward directions. Okay, to get the rotate, like the right or forward direction, we just multiply the rotation by the vector we want, or by the direction we want. So for right, I just multiply rotation by right, and forward rotation times forward. Okay, also we declare a new variable, local variable, and call it force. It's going to be set to the normalized vector of multiplying the right vector by the horizontal movement input, plus forward multiplied by the vertical movement input. And then the whole normalized vector will be multiplied by the movement speed. Okay, then we add force to the rigid body. By default, I think the force mode is acceleration, which is what we want. So we don't pass in any force mode here. Now we also check if we have jump set to true. So if the character or the player wants to jump, we just set the rigid body to, we add a force to the rigid body on the y-axis with the value of jump speed and force mode to impulse. Okay, so the character just jumps. Now we move down here to rotation. So we have the camera and the character itself to rotate. So usually in games, you rotate the whole character when you are trying to look left and right, but only rotate the head or the camera when trying to look up and down. So in this case, I'm declaring a local variable and getting the local Euler angles of the camera, which are basically the X, Y, and Z rotation. I'm declaring a float variable called pitch, which is going to check, is the current Euler angles on the x-axis more than 180, then it returns x minus 360, otherwise it returns the Euler angles dot x current value. Okay, this is to prevent the camera from snapping around or just being weird when you look up and down. Okay, and then here we assign the pitch to be equal mathf.clamp pitch minus pitch times pitch sensitivity, because when you look up and down, the camera, like the mouse input, is inverted, so we subtract instead of adding. Then we clamp it to something like -67 and 67.5. Now down here we assign the x property of the camera local Euler angles to be equal to pitch. If it's less than 0.0, we add 360 to it, otherwise we just set it to the current pitch value. Now camera.local Euler angles here will be just assigned the local variable we modified above here, so we look up and down. Now for the rigid body itself, we just rotate it on the y-axis by getting its current rotation and multiplying it by another quaternion, which in this case is going to be quaternion.Euler, passing in the value of yaw and the yaw sensitivity. Okay, the yaw multiplied by the yaw sensitivity. That's it for the replicate method. Now let's go to the reconcile method, which is extremely simple. It has a special signature as well, which needs the channel to be passed in as unreliable. And again, this parameter is automatically supplied by fish networking, so you don't have to do anything in regards to it. And also we need to have a data structure passed in as the first parameter of type, that implements the reconcile data. Okay, now going down here, we move our rigid body, both position and rotation, in a single call using move, which is different from move rotation and move position in that it changes both of the values using one call, which again saves performance. We pass in the position and rotation we get from the reconciliation data, and then we set the velocity to the current velocity we got from the reconciliation data, and same for angular velocity, we set it to the value we got from the reconciliation data. Okay, And that's pretty much it for the first person character controller. Let's test it one more time by going in the editor, doing a quick build. And as you can see, I'm just going to minimize this. I'm going to start a enter play mode in the editor. I'm just going to minimize this. I'm going to start in here, I'm going to start the server. So start server and client. And I'm going to start a client here. As you can see, we spawned and we can move around by looking up, down, left, right. Okay. We can jump, we can push each other, and that's it. Same goes to the player we just created, we just built. We can look around, up, down. We can go and push each other, as you can see. And yeah, that's pretty much it. I'm going to include the source code of this project in the video description if you have any questions. And I hope you enjoyed the video. If you did, please leave a like and consider subscribing. Thank you for watching, and I will see you in the next video. Bye bye.